Hello. Hello, everyone. Welcome back to the AAS YouTube channel. And this is the ebook series. And I am super happy to have ebook author Gibor Basri with us today. Hello, Gibor.
How are you, Frank?
I'm doing awesome on this September 11th of 2023 as we record this. And I think we got a sunset yesterday in Phoenix, just like the one on your background there. Where is that sunset taken?
Now, this sunset was taken at the Berkeley Marina.
Very nice.
About 15 minutes from my house down by the bay. That water is the San Francisco Bay.
Very cool. Very cool.
Yeah,
So you get a short walk.
You get really good ones.
Yeah, it's beautiful. Awesome. Yeah. So we're going to talk about one of your ebooks. And I'm curious, what gave you the idea to do an ebook? Where did that generate from?
You know, I'd been thinking about it for a couple decades. One of my colleagues wrote a textbook, and it took 2 years, and it was really a lot of work and so on. And so I didn't want to spend the time on the book while I was, deep in my research. And I kept waiting for somebody else to write it, because in the field of stellar activity, we didn't have an introductory book. So every time I had a new student, I was like, oh, well, yeah, I should give you some introductory material to read, but actually I don't have any. So here's some AppJ articles, and you're not going to understand most of them, and we'll start from there.
That's a trial by fire kind of approach.
Yeah, which I didn't like, and so I kept hoping someone was going to write an introductory book. And then finally I retired, officially anyway. And then I thought, well, so I suppose I do have time now if I choose to. And then the pandemic hit, and like, okay, I'll be home a lot, working on stuff. Now's a good time to do this book.
Very good, very good.
So I just did it.
Very awesome. So how long? So once you got to go, so how long did that take to get to, let's say, the finished product? Was that like a 1 week over the pandemic, or was that more like a 6 month, or where were we?
Yeah, more like 1.5 years, actually.
Yeah. Okay.
So I fortunately I didn't have to fight with a publisher so much. The IOP series was happy to take it on. There's a bit of review process. They try to check around, see if there's already a book like that. They send the proposal to a couple of folks. What do you think? And all that went very smoothly and quickly.
Awesome.
And then I just started writing the book a chapter at a time. And I wanted to make it concise, which is that's harder than just writing everything down. So it's not a review, it's an introduction.
Right.
So the question of what figures to put in there, which papers to cite, and so on. I spent a fair amount of time thinking about it.
Yeah, absolutely. Very cool. Very cool. Very nice. And that's going to bring us to this very awesome ebook, An Introduction to Stellar Magnetic Activity. Gibor, take us away. Got a lovely image there of looks like a coronal mass ejection.
That's the active sun. There's probably a coronal mass ejection, although I think what you're looking at is a flare, really, an eruptive flare. So it probably did produce a coronal mass ejection. Yeah, but the sun is actually a relatively weak version of stellar magnetic activity. So it's a cool picture, but I wish I had a picture of a really active star.
There we go. A little envelope going boom.
At least we think it would be amazing. We have never seen one.
Yeah, that's true. Directly. Very cool. All right, so let's go through it a little bit. Intro to stellar magnetic activity and intro. Okay, Ethan is the editor-in-chief of the AAS stuff. Steve Qualler heads up the editorial advisory board. We have a beautiful shout out to your SO there. I encourage people to read that. It's very beautiful. Very nice. And after a blank page, we come to the table of contents on Introduction to the Magnetic Sun.
Yeah. So that's a very short chapter. You actually, it's funny, you can't tell how many pages any of these things are from this kind of table of contents, but it's just 2 or 3 pages. The whole book is like 180 pages, at least in its physical version, which, so I should, I guess, mention that there's the ebook version, there's the physical version. And I probably shouldn't mention, but I will, that if
Please
you're
do.
poor and can't afford it and so on, you can contact me and I can get you a version. Because my purpose in writing this book is entirely to provide either students or researchers in the area with a nice introduction. Maybe you work on a particular topic here and you'd like to know the broader field, or maybe you're just starting. And so my only interest is that people would use this.
Yes.
No interest in income, although I did get an advance, so I admit that there was a little bit of remuneration as well.
Cool.
So it's just the first chapter is just really just talking about the sun, which is our touchstone for all of everything that's being said, at least in this book. I usually, when I'm doing a research project, I think about what does the sun tell me about this before I start working with stars. And the basic structure of the book is to go through the magnetic parts of the atmospheres of magnetic stars, so photospheres, chromospheres, transition region, and corona, and then to talk after having introduced all those things about what we've been learning about these things.
Cool. Very nice. Fields and other stars.
Yeah. So the chapter 5 is actually the sort of history of the field, starting with calcium measurements, actually starting with the first detection of a flare on an M dwarf, which happened at the beginning of the 20th century, and going all the way up to current research, which is already not current. As I say in the book, this is an active field. And so the chapter gets up to the point where things were in 2020, and already there have been advances since then. So, but this book is an introduction, so that's fine. Now you can understand the advances more easily. And then, so that's the evolution of stellar activity. But then after that, I talk about we'll come back and go through the chapters in more detail.
Okay.
You just lay out the structure of the book.
Sure.
So chapter 6 is then about, can we actually measure magnetic fields on stars, and what do we think we're looking for?
Yeah.
And as I tell students, the field is generated by a dynamo. Almost all proposals in the field of stellar magnetic activity say, I'm going to study this and we're going to learn more about dynamos.
Yes.
They still say that 40 years after I started this field, and we still don't really know exactly how dynamos work or what kind of dynamos work on which stars. And so that's that's at the heart of it in some sense. In another sense, what's going on below the surface is just producing these fields. What's perhaps more interesting to us is what do the fields do when they get to the surface, and especially now that exoplanets are a big thing. What does the stellar magnetic activity do to the planets around it?
Right. Yep.
So it talks a little bit about the theory of dynamos and cycles, and then the techniques of measuring actual fields on stars. And then the last chapter is a quick look at some other topics. So the main part of the book is really about sort of solar type magnetic activity. And then, as you can see, I look at, so I was involved in research on brown dwarfs. So what happens as we get to really low mass stars and then into brown dwarfs. I also, before I worked on them, I worked on pre-main sequence stars, T-Tauri stars. They're probably the most active stars that that are still not dead. Magnetars and things like that have stronger fields.
They got a ways to go, but yes.
And then post-main sequence stars, so subgiants, red giants, asymptotic giants, they turn out to have magnetic fields as well. Even we used to think that once you went to early F and hotter stars, you didn't have magnetic activity anymore because they don't have convective outer envelopes. But it turns out they do. They have also magnetic fields, obviously due to different processes. So there's a little bit on those, and then you really don't say too much actually about the effects of stellar activity on exoplanets, because there's a whole book on that and a lot of other stuff. And I guess that's a good time to mention the papers I chose to cite in this book. I cited either because they had a very, very nice figure that I wanted to use, or they were sort of reviews themselves, or cited a lot of other good work. And so the book is also intended as a place to find pointers to details on all this stuff.
Yeah, very good. Very cool.
It's also probably worth mentioning that there are very few equations in this book. It's not intended to be a textbook. It's intended to be an introduction. So I'll point at where you can find all the mathematical details and other details. But I'm trying to just describe the basic physical mechanisms, the basic physical effects that are interesting, and then point you, if you want to know more about that, there are certainly references to where to find more.
Good. I bet one or two of those equations show up somewhere when you talk about magnetic dynamos, I bet.
Yeah, well, actually, so there's I guess it wasn't, go back down again.
Sure.
Oh yeah, Appendix A. It doesn't really say what Appendix A is about.
Yeah.
Most of the equations are. Appendix A is a basic concepts of radiative transfer, right?
Absolutely.
So that's of use if people want to understand how we use spectra to get the physical details on stars, especially in this particular area. So it's complicated. It's not just there's LTE, local thermodynamic equilibrium, radiative transfer, which is relatively simple. And then there's non-LTE radiative transfer, which it turns out is more appropriate for many of the chromospheric lines and so on that we use. And so I think this is, and a lot of people find radiative transfer to be a rather difficult subject. So this is just a few pages of the essence of it. And I like to think that it's relatively readable and comprehensible. It's just the top level stuff.
Yep, very good.
And I try to explain why these particular things are important. And then that's it. So, but I did write the book, so you don't actually have to read this chapter if you don't want to. It mentions when I'm talking about something that's explained in the appendix, I just say, well, so if you want to know what I'm talking about here, read the appendix. If you don't want to know, just keep going.
Carry on. All good.
Crucial.
It's all good. Very good. Okay, that's the mystery Appendix A. Very good. Yeah. Cool. Well, that's okay.
So I don't know. I can briefly go through what's in the rest of the chapters here.
If you like.
Physical structures in photospheres is basically about either spots or faculae. So these are physical structures that are caused by magnetic fields. Yeah, sure. There's some nice pictures. We can just do the pictures.
There we go. Picture two. The
famous one. Yeah,
famous one.
Here's a picture of on the top faculae. So all those little bright things there.
Yep.
Are what are called faculae. They're really a fun structure in the sun. So when you look at the sun straight on, you don't see them. And they show up more towards the limb. And there was, for a long time, people didn't quite understand what they were. The dark things in the upper picture are what are called pores. They're sort of small sunspots or developing places where a spot might occur.
Cool.
But the faculae are actually the sides of granules, convective granules, that have been sort of shaved off optically by magnetic field.
Okay.
So you see inside them a little better where it's hotter, and that's why they look bright.
Yeah, very nice.
Those are the faculae, and then of course there's a sunspot in the lower picture. That's a nice high resolution version, so you can see the dark stuff is the umbra, the threads around it are the penumbra.
Yep.
And then the rest of the modeling there is of course just granulation, regular convection.
It's my favorite Van Gogh sunflower shot.
Yeah. Okay, let's go on up. Maybe we can just go through the book by pictures.
Okay. So where are we at? Let's see. We covered some of the photospheres.
Oh, well, yeah, I mean, well, I don't know. Maybe it'd take too long to just go on down through the book, stopping at pictures.
Okay, well, why don't we do, let's see what we got in chromospheres. Let's go to chromospheres. Chromospheres, there's a nice chromosphere.
Yeah, there's an H alpha picture of the chromosphere showing that it's much more structured really than the photosphere. So in the photosphere, the gas pressure dominates the magnetic pressure, but in the chromosphere, the magnetic pressure dominates the gas pressure, and so the atmosphere takes the structure of the field more or less. And of course, at the limb, you can see the prominences. Those dark threads on the disk there would look that way if you turned the sun so that they became edge on.
Okay.
And there's actually, I think, a flare going on in the lower right there, where the H alpha is nice and bright. So that's magnetic reconnection, heating things much hotter.
And there's a simple subject. Very cool.
And why don't you go on up?
Chromosphere. Let's see what our next one is. Chromospheres. Transition regions.
I don't want you to jump quite that fast.
Oh, sorry.
So let's go to section 3-4, for example.
Okay. I'll go a little slower and go down. How about that? 3-4. Semi-empirical.
Right, yeah. But let's find a picture.
Let's find a picture. Ooh.
Okay, so this is the temperature structure of the chromosphere. That's it's right. Your outward is to the left in this picture, and it shows the different diagnostics that we use to infer what's going on at these various levels in the sun. So you can see it's a very multi-wavelength thing, and some of the diagnostics are spectral lines, like the calcium K line you're on there, and some of them are continua, like the silicon 1 continuum at 152.4 nanometers. And so the book describes a little bit about how we use those diagnostics and what we've inferred about the structure of the chromosphere. If you can roll up a little further, we'll look at a spectral line or spectrum of some sort. There we go.
There we go. Here's a spectrum of the upper. There we go.
So those are some spectra of looks like the H alpha line. Those are from different stars now. And in addition to the observations, there are some models there. And so we talk about how we do these semi-empirical models. They're semi-empirical because the chromosphere is so complicated, we don't really know how to model it from first principles. And in any case, the magnetic field is kind of all over the place and changing all the time. So we have to use these simplistic semi-empirical models to try to model what we're seeing in the actual spectra.
Very nice.
Okay, maybe that's enough for the chromosphere.
Okay, and where are we here? Let's just slide down 4. Ooh, I like that.
Now you went through the transition region. Okay. Now we're in the corona. So this is a nice explanatory figure about what the structures above the sort of visible surface of the sun look like, how flares happen. And there's a discussion about how flares work, which we're still working on too, of course. But so it turns out magnetic reconnection, of course, is very important all around astrophysics, and it's pretty complicated. And the sun is probably our best place to try to study how it really works.
Yep.
And so we talk about that some.
There's 4 there.
And we went by, there's pictures at different wavelengths that show different levels of the solar atmosphere in chapter 1. And actually I show the same same time on the sun at a bunch of different wavelengths. And basically, as you go to higher energies, you are scanning higher and higher up into the solar atmosphere and above it. So these loops that you see there are sticking out above the solar surface, but they're lit up in the ultraviolet.
Nice.
And so on.
Very nice. Cool. Okay, section 4, stellar winds. Guess we'll do section 4.
Yeah, then above, of course, above that, you've got the solar wind, and it extends out into the solar system. There's a CME. It's a coronal mass ejection on the bottom there. Sort of view of how the magnetic structure of the sun sweeps out through the solar system. And of course, this is of great interest to exoplanets because especially exoplanets around low mass stars will be much closer to the star. But it turns out that the magnetic activity on those stars is at least as strong as it is on the sun. Only now you put the planet way closer, and so that's why it's a real potential issue for exoplanets.
Indeed, at least life on exoplanets.
Well, yeah. Well, even sometimes atmospheres on exoplanets.
Oh, sure, they're gonna get smoked, right? Yeah.
Or whether you can retain your water, for example.
Yes.
As Venus didn't.
Oh, poor Venus.
Okay, go ahead.
Yeah, let's see. So we'll do. Let's walk through. Let's do. Ooh, so there's some of our references.
Okay.
Chapter 4, and then we head into.
So now this is basically the history of the field in essence. So it's the beginning of a series of stellar activity, blah, blah, blah.
1895.
Yeah, that's that was when the plate was taken. It wasn't actually analyzed until the early 1900s.
Wow, really? That's amazing. Okay.
But they saw that H alpha got bright on this red dwarf.
Okay. Very good.
But,
let's go down and find.
Yeah. Then now that's a description of sort of how we came to the idea that one of the main things in stellar activity is rotation activity relation. So it turns out that if you spin the star faster, the dynamo gets cranked up more and you get more magnetic activity. So the discovery of that, these are the middle plot is the log of the rotation period, and the y-axis there is a measure of activity. The stars on the right are sort of evolved subgiants, and on the left it's main sequence stars. And people still argue about, the top plot is a Rossby number plot, so everybody tends to plot activity against Rossby number, but the book explains that that seems like a great idea and it sort of works, but actually there are other ways that work too.
Yes.
Middle and bottom plot. Good. And it makes theoretical sense to talk about Rossby numbers, but if you want to go calculate them and do they really work, it's more complicated than you might think, I guess.
That's a fair statement. That's a fair statement.
Rossby number is the ratio of convective overturn time to rotation period.
Yes. All right. Think about convection. Very good. Okay. Let's slide down a little more.
So those are various rotation activity connections, and then I get into the subject of gyrochronology. So, in principle, you could if you go back up a bit to that figure.
Okay.
Right. Yeah, that one. Right.
Okay.
So there you have the rotation period on the y-axis and a measure of stellar mass or temperature on the x-axis. And
minus V.
This is for different clusters like the Pleiades and M35. And basically what we see is that stars spin down over time. So when they're spinning fast, they have strong fields. The strong fields generate strong winds. The winds are magnetic, and so they carry off angular momentum basically. And the star, is trying to spin the wind around, and so it's losing angular momentum. So they spin down. And the subject of how they spin down, how that depends on stellar mass and age and so on, is like a very current topic. But in principle, you could, if you knew how that worked, you could tell how old a star was based on how fast it was spinning. if you
Yep.
knew its mass, for example. And whether that really works, I mean, it definitely works down to about the age of the sun.
Okay.
People are still arguing a lot about whether it works after the age of the sun. And you might say, well, we know other ways to find stellar ages, but actually we don't. For stars that are less massive than the sun, they evolve so slowly
Yeah.
that their position in the HR diagram or the isochrones don't really help you much. So gyrochronology or just the measure of how much activity is on the star can be a good way to get ages for lower mass stars.
Nice.
Anyway, so that's a very current topic of research.
Yay. Nice. See, it's a modern book. Gyrochronology.
Gyrochronology, yeah.
And we'll go down. It's at least one equation. Okay, let's get my hand on my slider here. Let's move on down. This one looks good. Rotation behavior of different stars.
So the other thing that's happened in the last decade or so is we've gotten a lot more stellar rotation periods. The Kepler satellite, which I was involved with, was a particularly good source for those. I just was an author on a paper where we published 67,000 rotation periods.
Wow.
And in particular, you can try to get rotation periods for a bunch of stars in a cluster. So now you know what they're all rotating like at the same age, and that's what this plot shows. Shows different clusters, different ages, and how their rotation periods are arrayed against the masses of the stars in the cluster. So that's how people study this.
Cool.
There's definitely an organized process, but it turns out to be rather detailed too. So
right, so you can tell some broad trends, but there's a lot of features.
yeah, and it's not fully explained yet. So this is a topic of current research.
Beautiful. 67,000? Wow, that's a lot of periods. Okay.
Yeah, so that was more clusters, but let's move on.
Let's move on to, there's our references for chapter 5, and then chapter 6, stellar magnetic fields.
So this is about the fields themselves. So the first part is about dynamos, which is how stars generate these fields.
Mean field theory. Here we go.
And there I just explained that sort of the kinds of dynamos people think are operating. This is a changing field also. So these are numerical models of stellar fields being produced.
Global.
And to actually compute how a star produces fields is beyond us, basically. So you have to make a lot of approximations and treat it various ways. And so the book just sort of introduces you to the way people attack this problem, some of their results, some of the issues that are still around. So it's intended, as I said, as an introduction.
That's a good one. 2015. So we do some dynamos and stellar cycles.
Everybody knows about the solar cycle.
Yes.
But we know a lot less about cycles on other stars. So that's the sunspot butterfly diagram and number of spots.
Yes. Classic.
That's classic, but then we don't have that kind of data for other stars very much at all.
Soon.
As you can see, you want a long time span of observations.
Well, okay, that will take a while.
We really don't have that. There are, we know cycles on maybe 50 stars reasonably well, and we're of course accumulating data as we go on.
Very nice. So we get dynamo cycles.
We know a little bit about butterfly diagrams from actually transiting exoplanets, crossover spots, and there have been a few cases where we can actually track where the spots go, or some techniques that are further down in this chapter allow us to sort of image where spots are.
Okay.
So let's keep going.
Let's keep going. Let's slide down. Direct measurement.
So those were stellar cycles that you just went by.
Okay, so how do we actually measure it?
So how do we actually do it, right? So there's a little bit of a explanation of how Zeeman techniques work. That's on the right there, that line that splits into 3 there, that's because of Zeeman. splitting
Mm-hmm.
to the magnetic field.
Nice, very good. Ooh.
Yeah. So on the sun, you can spatially resolve all this stuff. So you get magnetograms, and we know a lot about what the surface fields on the sun are doing, but you can't do that with another star, at least certainly not at that level of
not at this level of detail. That will be a while.
And it turns out you can do a little bit of that, so that's explained a
Mm-hmm.
little further down.
Okay, we do some
broadening in stars,
and here we got some other stars here.
So there's some spectral lines which are broadened by magnetic fields, and you can infer something about the magnetic flux on the star there.
Lauren Linsky, 1985. All right. Very nice. Down,
this was a method I invented where you don't have to resolve the line. You can just measure its equivalent width. And because of the radiative transfer, if the line is saturated when there's not a field and the field starts moving the components apart, it can be desaturated, and so you can get a stronger equivalent width just because you have a magnetic field there. There you need to have a spectrum that's got lines that are sensitive to the field and lines that are not sensitive to the field, so that you can see that this effect only happens in magnetic lines, magnetically sensitive lines, and then you can infer a field from that.
1992
method.
Check it out, 1992 right there. All righty. And we'll go down magnetic polarization. And
the other way to do it is with polarization. So using Stokes components of the spectral line.
Yes. Let's do
that explains how that works.
Let's see how this works.
So there's a spot, and then with one polarity at the top there, spots of opposite polarity in the middle there, next to each other, and spots of opposite polarity on top of each other, sort of latitude. And you can see they have different effects on the spectral line that you would measure, and you can then run with that and actually try to make a map of where the magnetic field is on a star, if you can measure this polarization signal. And that's gotten a lot of play in the last 20 years or so. There's some excellent instruments that are measuring this kind of thing now.
Sort of
so a little further, you can see the kind of map you can get out of this.
Let's go a little farther there. Let's see. Maps. Here we go. The three components. Solar star.
So there's
1156.
There's the kind of mapping you can do. Turns out, however, though, that this method only can measure the polarization if you have very large scale fields. So if you have small scale fields, the positive or the north and south polarity, however you want to call it, will cancel each other out in the polarization signal. So in essence, what you're seeing here is the uncanceled flux. And you measure the broadening of spectral lines to get the full flux, and it turns out that these uncanceled fluxes are 10 to 30% of the field on the star. The rest of it is getting canceled off.
Interesting.
But you can get that from the broadening of the spectral lines. So put them together and you can start really doing something with it.
Very nice. Very nice. Yeah, we go down here. Rotation.
I don't want to explain that. That's a confuso diagram. But
that's why it's at the end of the chapter. Onwards. Stellar magnetism in other contexts.
In other contexts. So that is meaning non-solar type stars, basically.
Okay.
So the bottom of the main sequence, for example, turns out stellar activity dies. When the star gets too cold, you don't get activity anymore because the motions in the photosphere are no longer coupled to the magnetic field. Like the Earth's atmosphere is not coupled to the Earth's magnetic field. And all the activity that we get is caused by the motions of the gas moving the field into configurations it doesn't like, and then reconnection happening, waves happening, and heating of the plasma, and that's what we call stellar magnetic activity. So if you don't couple to the field, you're not going to get that. So it
Yeah.
turns out it's right about the bottom of the main sequence where this just kind of dies.
Yes.
Yeah. On the other hand, the stars, we were able to show that the stars still have magnetic fields. They're just not generating activity.
Fair enough.
The sort we're used to. So
fair enough. And
another dying.
Yep, down she goes. All right.
Yeah.
Very cool. Looks like one of your plots from 2008.
This shows that the other effect of that is that since the star is not able to lose angular momentum through a magnetic wind,
right,
but it does contract onto the main sequence, or contracts when it's forming, it'll spin up and then not spin down. So the gyrochronology thing doesn't work, and what you get instead is really rapidly spinning stars. So I was also the discoverer of this effect. Once the Keck telescopes came online, first thing I did was look at the faintest, the coolest star I could think of. I couldn't understand its spectrum. It was you couldn't see any molecular lines. It was very weird, and it took a few months to figure out that this star had a rotation period of a few hours.
Oh my goodness!
way different from
okay.
stars we're used to. And so this plot just shows that velocities get pretty strong. Now everybody's used to the idea that brown dwarfs and very little mass stars are very rapid rotators. But
well, congratulations on that discovery. Yeah. That was awesome. All righty, and so near the bottom of the main sequence again.
Yeah.
Okay, let's slide down. X-ray.
This is X-rays and radio. So this is another way to see that, for example, coronae go away. But there's still radio emission. And now we think that some of these stars have like really strong self-induced aurorae, but not coronae. So they're not bright in X-rays, but they're bright in radio.
Yeah. Okay. Very good. Very good. Pre-main sequence.
Yeah. Now we just talk about pre-main sequence stars, which of course the sun was at one time. And they are extremely strong magnetically active stars. And in fact, the magnetic field influences the way the star accretes material. Once the star gets going, it generates a strong enough field to actually interrupt the disk. So we actually think this is why you get hot Jupiters. The disk may be trying to drag the planet into the star. When you get a strong stellar magnetosphere like this, the disk suddenly is gone, and the planet can stop there.
That's one way to stop migration. Absolutely. Yeah. Very good.
Kind of fun.
Sequence
and those fields are very strong and very variable. So it's the first decade I was doing astronomy, I had a lot of fun just taking spectra of T Tauri stars night after night, because every night it would be different.
Yeah.
Now there's a lot of good modeling and so on about what's really going on there, but so that happens on very human timescales. So
I was going to say, yes.
Yeah.
Night to night, very good.
And we talk about post-main sequence stars. So after the star evolves off the main sequence, it's still rotating and it's still convective, so it's still going to have fields. This is a particular fun kind of active star called RSCVN systems, where you've got an active binary with at least one evolved or two evolved stars. Yep. And they're close enough that they can actually interact with each other. Occasionally you can get a flare that crosses from one star to the other. Those are fun systems also.
Very nice. B fields. Okay, AR Lacert, RSCVN, sort of our schematic, we'll call it.
It was a schematic, but based on X-ray observations where the stars, cross in front of it. This is an eclipsing system, so we were able to tell where different things were.
Nice. Lucky that one. And then we move off and we go into the hot side of the things.
Yeah, so hot stars we didn't used to think would have fields, but actually they have even stronger fields sometimes. Some of those are just primordial because, of course, hot stars don't live very long, so they don't have to keep generating field.
Fair enough.
But the A stars are weird. So For those stars, the outer part of the star is not convective, but actually the nuclear burning core is. And so some theories produce the field in the nuclear burning core and then let it come out to the surface. But they're not the same as the solar type fields, and you don't get the same kind of activity.
Correcto. Very nice. DDI maps. And we'll slide.
That's just about it.
MHD model. Definitely.
Yeah, this is an O star that's got strong fields, and there, of course, the wind is generated by the luminosity of the star itself, but it can still interact with the field.
Okay. Ooh, wow. Very cool. Nice work on that one. And then the effects.
And finally, this is a huge topic which I don't do justice to in the book because there's so much other stuff written on it. There's a whole book on this topic.
Indeed.
So I just mentioned that it's really interesting and that you should go look at this other stuff.
Very cool. And then we walk into a reminder.
We've already talked about Appendix A, so I think we're done.
Very cool. Very nice. Gibor, I want to thank you so much for walking us through this very awesome ebook. Where's my title? There we are. There we are. Thank you so much. So go get a copy, people. Learn a little bit about magnetic activity. Awesome. Very cool. You mentioned it a couple of times as you went through, or lamented, or something along those lines, of material that was missing or maybe not quite synthesized yet. So is there, not that we need another pandemic for you to do it, but is there going to be a version 2 at some point, or do you envision that, or what do you imagine?
I don't envision doing that myself. I think, we can wait 10 years. As I said, the field is advancing in various ways. So I think what's covered in the book is a pretty good synopsis of where we have gotten, at least by 2020. And I would think that, by 2030, there would be enough new advances that one would probably want to add to that. I've been waiting for folks to write me and say, oh, you got this wrong, or you should have talked about that, and so on. So I encourage people to do that. I haven't gotten too much input so far, so it seems like the folks who I know who've read it said, "Oh yeah, that was what I was looking for."
Very good.
But yes, I think in a decade it would make total sense to add, whatever we've learned by then, which is definitely happening.
And in the meantime, it is an outstanding introduction. So go grab a copy. Cool. It's really awesome. Gibor, thank you so much for walking us through your very lovely ebook, and that will do. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Thanks for having me.
Oh, thank you. Okay.